So for today, what I'm going to be talking about is just kind of almost a code review. It's not really a presentation per se, but really we're just going to look at a few segments of the code that I've pulled directly from the working draft, which is a pretty long document. I definitely suggest you read it and just kind of look at the code and see if it makes sense to everybody and why it's useful. So I will open up the README here. I'm not going to read through this whole README because it does contain whole sections of the draft document. It's a lot of text. But basically, if you're not familiar with generics at all, like if you're coming from a JavaScript background, or maybe you've been using Python for a long time and maybe not using some of the generic features that have been added relatively recently, as far as type hinting and the typing packages in Python. But generally, generics are a programming paradigm that are useful for when you want to design algorithms or data structures that operate over types that you don't want to concretely specify when you're writing the data structure or the algorithm. And what I mean by that is that the types are parameterized, and that's what the name of the Go design draft for generics is called. I think it's just, the document is called Type Parameters in Go or something like that. So why is this useful? Well, you can imagine that if say you're implementing something like Go's map, like a hash map, or a hash table in any other programming language, you can naturally say you want to have a map of like string to, say, an empty interface. If you want to have it be a string that can be marshaled then to some other concrete type, or you could say it's just a map of integers to other integers. You can do that very easily. But if you wanted to write a generic map and say, I want a map of keys, where it's just a type K to some value, type V, and you want the compiler to figure out, okay, well, you tell me the constraints and rules around what K and V have to behave like, and then I'll figure out what concrete type makes sense for your actual implementation. And that makes things very useful when you're trying to do a few different things. There's some examples that they point out in the draft design are if you want to implement generic Mapreduce and filter operations. If you come from a functional programming background, you know that that's something that doesn't really exist in Go. You can implement these things right now, but there's a lot of boilerplate and it's kind of annoying. But you might want to say, well, I want to take a slice of items and I want to map over each item and apply a function to that and collect everything up into a new slice and do something else with it. There's a couple of other things. There's sets in terms of unique elements within a map. There are the ability to generically sort over anything that sort of conforms to the constraint that they call ordered in the draft document. And when we get through the code samples, this will make sense. You can say, probably the thing that we have the most direct experience with at my work has been generic operations on channels. So as I mentioned, we work over graph databases, and we have a large part of our core technology is being able to stream over large amounts of data. And we've had to implement basically real-time streaming libraries in Go. And it's unfortunate that in order to get sort of the flexibility that we've needed, a lot of times these end up being streaming channels of interfaces to other interfaces. And it's just, we lose a lot of the strong static typing that makes Go a pleasure to work with. So this would have definitely helped us. And there's some other examples that are more, sort of code golfy, to just say like, you have to copy and paste less, or you have to do less type switching, things like that. I won't cover these approaches comparing with other languages, but it's very interesting. The Wikipedia entry for generics is very good. If you read through it and you just see, okay, how has this been implemented in languages over time? It's fairly interesting. As I mentioned, Go's proposed implementation of generics is actually pretty similar to Rust's. And there's some takeaways and some helpful links, hopefully. So with that, I will just jump right into some of the code examples. So is this text size good, or should I make it larger? Is this good for you all?
You can make it a little larger.
All right. How's that?
Yeah, that's perfect.
Looks good. Yeah.
Great. Okay. So this will actually run, and I'm going to run it first, so you can see the output, and then I'll go to the implementation. So this says hello playground 1, 2, 3. Not that interesting. But what we can see here is this print function has some new syntax. So basically what we're saying here is that given a generic type parameter t, we want to call print on any slice of t. And as long as it is a slice of t, then it will print. And so what we can do is we can say print on a slice of string, say hello playground. We could say print on a slice of ints, and it just works. This is currently not possible in Go right now because we don't have a way to specify this type parameter here, any. And I'll talk a little bit about what any is, but basically any right now is loosely considered a syntactic sugar over an empty interface. And we'll see why that makes sense when we look at how the implementation is actually done for constraining types. So given that we can say there's some type parameters that mean something. Let's say we want to stringify something. So you would read this as stringify takes a t, which conforms to any, and it operates over a slice of t items and returns a slice of string. So we try to do this, we call the string method on it. This actually doesn't work. And this is worth seeing why it doesn't work. So we get type checking failed for main. So here we're kind of seeing how the proposed implementation will do type inference. And so basically the error is saying it can't sort of confirm that the value that's within this slice of t actually conforms to the string, the interface that supplies the string method, if that makes sense. Does that make sense to everybody why this fails?
I think it's clear.
Okay. So now this is just a normal Go example, and this sort of introduces how the authors are implementing the proposed generics execution. And it's simply to use Go's existing interface type. And this is useful because it means that if the proposal goes through, and this is how Go does end up implementing generics, it'll be completely backwards compatible with existing Go code. Because basically they're just slightly expanding the role of how interfaces are able to be transformed later into concrete types. And so interfaces are the way that you actually provide the constraints on your generic types. And this has got nothing to do with generics. This is just a normal Go implementation of an interface. We just say we have a stringer that produces a string, we have a concrete type, we implement the method on it, and then we can call f.string. That's totally straightforward and should not be surprising to anyone who has written Go before. And so this is what I mentioned before, where you the keyword any is syntactic sugar for empty interface. And this is actually useful for more later on, more complex examples that you see in the design draft, where you can say any if you just want it to be an empty interface, the way that we're used to doing. But you can also actually specify methods on an empty interface here. So you could say, I want to print any t that who satisfies the interface that has this particular method, and you can actually provide the method signature here in a literal form. I don't show an example of that just because it's not all that useful, and this early on it might be a little bit confusing. But this piece is just to show the syntactic sugar. Any just means empty interface at this point. They do mention in the design draft that they may want to make this sort of language wide, where any place you would normally write empty interface, you may be able to provide the any keyword, but that's not. They say that it's not within the scope of the design draft. So if you see later on when they actually do implement this, if the any keyword If you see that, then you can understand it to mean the empty interface if they do end up implementing it that way. So when you see any later on in the code examples, that's what it means. So going back to the example that didn't compile. So if we know that stringer is an interface, and we know that the proposed implementation of generics uses interfaces to constrain over the generic types, now we can understand what this type signature means. So we can say when we stringify something that it takes anything that is constrained by the stringer interface, because now we know that interfaces constrain generic types, and we return a slice of string. Now, because they're using interfaces that we're all familiar with, interfaces can also be, different interfaces can be parameterized at once, like this. So we can say we want to concatenate to an S that satisfies stringer and a P that satisfies plusser, and we can operate over those types as we would expect. Everybody with me so far? Good. So more sort of syntactic things to understand. When we instantiate generic types, we can say that a type of vector, for example, if we want to create a generic slice, we can say a vector of T that conforms to anything. It's called a slice of T, and then we can make a concrete instantiation of that generic type. And this would be very familiar if you've ever written Java or Rust and you want to create a concrete type from a generic type container. This is how it looks. So that syntax hopefully should be pretty familiar. And just like any other concrete type, we can also add methods to the concrete implementations of, we can add methods to the generic implementations of these containers that we're building. So for a more sort of concrete example, and to show one other sort of edge case that you have to think about when you're talking about the current draft is, let's say we want to create a singly linked list. So we can say that generically we want a type list of anything that has a pointer to another list that it conforms to the same constraint and has some value. These are all T's. This section of code is added to explain that the type parameters have to be passed in order. That's important because of how the type inference works. I mean, that's just an example of what not to do. And then types can be cross-referential, which we can be familiar with if you've ever, say you've built a graph data structure and you have a node type and you have another type that refers to a pointer of node or something like that. The same thing works across generics. And this is sort of putting together these ideas here where we say any element in a list has a pointer to another element and also contains a reference to the list's head and as well as the value at that particular node. It's all very straightforward, but it's worth seeing how the syntax sort of plays out in all of these different scenarios, just because if you're familiar with the way the generics work in other languages, it's good to see kind of side by side, like, does it work as you would expect? So let's see here. Now this is really important. So we've talked a little bit about how the generic syntax works. And that's very straightforward. That's also not really different than any other language that implements generics. If you've ever read generic Java or Rust or Scala or Kotlin, anything else like that, C++ templates are a little bit different. The README goes into that, but suffice to say, the syntax should not be completely alien if you've ever read any generic code. And even if you hadn't, it's very straightforward in relation to regular Go code. But aside from the syntax, the important question is, okay, well, how does the compiler understand how to transform your generic types into concrete types through interfaces? Like, how does that actually work? So the way to do that is what they call type lists. And type lists are basically you can say that your interface, and your interface can provide a given set of methods, just like it always does. But you can now add types to an interface. And what then happens is that you can write a generic algorithm somewhere else in the code. And as long as you pass in a type that conforms to that interface, that's explicitly listed in your type lists in the interface, then it will work fine. So this function doesn't work because what happens here? Well, we're trying to find the smallest element in a list of something, t. This would panic if the slice is empty. Maybe there's a better way to handle that. We do a length check or something. But the critical part is we're ranging over everything in the slice. The compiler doesn't understand how V and R relate in terms of how they're ordered, because there's no way to express sort of the ordered constraint right now in Go. And so that's where the generics implementation solves that problem. So this doesn't work because there's no understanding of what ordered means. So how do you know when something is less than or greater than something? So that's what type lists are for. So there's a couple of examples of type lists. So if you want to say a signed integer is only the types that are not uint of some size, you could say that. This is using a generic interface as sort of a type alias. So you can just maybe shorten your code so you don't need to write methods that operate over an int and an int8 and an int16. You can just say, okay, if anything is signed, then it will work. But the key to solving this smallest invalid function is this ordered interface. So this is, you're explicitly telling the compiler, when I say ordered, I mean any of these concrete types. And once we do that, and we pass in smallest and say that it has to operate over elements of type T, which are constrained by the ordered interface, then it all makes sense and it will work. Now they say constraints dot ordered here because the idea is that it's probably going to be the case that when the generics implementation is actually made concrete and a part of the Go language, they're going to provide a lot of these sort of out of the box interface constraints for us in a package. And they're calling this constraints right now for the purposes of the draft. So if you see constraints dot something anywhere in the draft document, or when you're experimenting with the code in the playground, that's what that means. So hopefully that makes sense, that we're able to constrain what the behavior of type T in terms of the generic over something that's described in the interface. Let's see, there's a couple of other things here. I thought it was interesting to go over how the type inference matches. And this is pretty straightforward. Basically, you say, if you have a map of integers to bools, you have that type. You can say if T1 and T2 are type parameters, that a slice of T1 matches that because T1 matches, well, T1 is a slice. Actually, you know what? No, I'm just going to skip over this part. This, I think this maybe was going to be fleshed out in a different way. I don't want to add any extra confusion. Does this all make sense so far? How type lists are used to sort of transform the interfaces we know and love into something that actually constrains over generic types? Does that make sense?
Yeah.
Yeah, I'm curious, is it possible for you to maybe execute a real small example? I'm curious what type of exceptions are thrown when you pass in a type that isn't part of the ordered interface and things like that.
Sure. Let's see. Okay, so let's say we did add uint. Let's see. Interesting. I don't know if the type, I don't know if the make slice constructor will work with the generic types. Interesting. Well, you just like
Oh, and if this is going to derail your
no, not at all. Here I'm trying to think about it. I'll do this. I'll just make a normal slice of units. Oh, actually, super simple. Let's do this literally. Let's see. Let's see if the type inference. This should panic with a type inference check failure, I think. Let's see. Yeah, that's right. Didn't make this a real package. Yeah, okay. So type checking failed. So that's what you get. And this is similar to when the stringify, or I think stringify was the name of the function, didn't conform to something that was explicitly defined in the interface. So that's the case here. So I removed uint from here. So a slice of uint doesn't conform to interface anymore. And that's one thing that they mentioned kind of later on in the draft document, but I think is important if you've written a lot of Go before, because one of the features of Go's interfaces is that you expect implementation to be done implicitly, not explicitly. So it would be easy to forget, I imagine, if you're building a more complex data structure that has a more complex sort of constraint interface, you might forget to add a particular concrete type, and then a user might try to call that later on and get an unexpected type check failed message like that. So it's a good experiment to see. It should work if the constraint is re-added. That's the same problem. So that's interesting. That's a good question.
And those are build compile time errors, not runtime errors. Those type checking errors.
That's correct. Yeah.
Okay. Yeah.
So like right now, the little shell script that I'm using is running. It's running Go it's running effectively Go run using the Go to Go tool, but it would be a build time error.
That makes sense.
Yeah, but that's a great question. So moving on. So moving on, they just have a few more examples of now that we sort of understand how the constraint system works, how these types are used. So we can say that you can double something if it conforms to constraints number, and you can modify the contents of that slice, return a new slice. Another thing that is interesting here is the type lists in terms of the constraints can also use other generic types. So that's an example they use here. And the reason they do this is, like, say you have a custom slice of integers that you want to have some special methods on or something like that. If you pass in my slice here to this function double, the return value can't be inferred from the constraint. So what that means is that if you call double on here using this slice of integers with a slice of 1, when you get back the type of v1, that's going to be a slice of int, because that's the concrete implementation. You're not going to get back a type of a slice e. So if you need to constrain the return values as well, or you need to sort of make sure that you're the way that you're sort of embedding the constraints from one interface into another. Again, just like with the type list, you have to be explicit about that. So that's the way that they model, the way that they resolve that sort of unexpected behavior, is to say, well, if you're going to double it, then you need to also specify what the special return value that you want is. And so the functionality is exactly the same, but here you get back the type S, which conform, like the type slice of E is constrained by it. So that's an important thing to understand, is that the way that the constraints work is very explicit. Basically, if you don't write it up concretely in the interface that you're defining, then the compiler is most likely not going to be able to infer how those things work. And because of that, when you do the double defined here, over my slice of integer, you're still able to pass in the literal because you're parameterizing the concrete type, and this will work, and you get back the type that you expect, my slice. And this can be inferred by the compiler. So this third example, they say, well, if double defined of this literal int slice will actually produce the behavior that you expect, because you constrained it explicitly. And this is good because, as once the generics implementation is finalized, obviously we're going to be using this to build packages that other Go developers use. So that's important. Like, I think the general gist that I've got from the way the code examples were laid out and everything is that just like with other things in Go, I think as the package authors, we're expected to be as explicit as possible to make sure that callers down the line are able to easily use the code and it won't surprise them. I think the principle of least surprise is very strong in the Go development community, and that's been shown through the way that this document was written. So do these sort of customized constraints make sense to everybody?
Mm-hmm.
That one. Okay, so let's look at some other examples. Trying to see which ones of these are actually interesting. Let's see. Oh, so this first example of setters and from strings is not that interesting. It's kind of what you would expect given what we've seen already. It's just added in the document because it's again sort of explaining how the type inference work and doesn't work. And so there are situations where you need to be more explicit about your return types or your parameterized types. But that's fine if you read the document, that will make sense. We haven't looked at pointers to these constrained generic types yet, so that's something that's interesting to cover. These are all relatively straightforward. We can say if we have some custom type settable, we can write a method for it, it's fine. But here, this is invalid. And it's the same reason as before, the type check fails. And the reason for that is that we haven't described a pointer to the generic type as being explicitly required by the interface. So that's what this setter2 interface does. And this is a new piece of syntax because now we can see that the interface itself has a type parameter. And if you've ever read or written any Rust, this would be very familiar to see an interface defined in terms of a generic type. In Rust, these are called trait objects. But basically, you are saying that a setter over any type that conforms to B has a method that takes a string, doesn't return anything. And critically, the type list is just a pointer to whatever B is. And once we do that, then we can again, as the package author, you have to be explicit about the parameter type. So they call it PT here, which really just means a pointer to T. But once we do this, then we can actually dereference the values as we would expect. So it's a little bit verbose, but if you read through it and you play with the examples in the playground, it will make sense. Let's see. This is a very similar example. This just has multiple parameters, which we've already seen. This one here, this one here, so this is just a syntactic convenience. If the second type parameter is a pointer to the same type, the compiler can infer that it's the correct type, that has the correct constraint. That's kind of just syntactic sugar. That's not that interesting. And then this is sort of the like a forced example of what we already saw twice, where type checks failed because something wasn't explicitly added, wasn't explicitly in the interface type list. So here we see the same thing. We can't call from string 2 over a generic unsettable type because it doesn't have the right method. It doesn't have the set method. So hopefully that makes sense. And this was one of the complaints when the draft was very first being written, I think like over a year ago now. It can get a little bit verbose. So sometimes you have to slow down and kind of think about the types like twice as long as you normally would when you're talking about how to constrain them by these generics. But I think it will make sense down the road, because even if you have to be more explicit and write a little bit more boilerplate yourself as the package author, I think it will make calling the code much easier.
You just touched on something that I have a question on.
Sure.
And I'm gonna admit I'm woefully behind in the fact that I have not read the entire proposal. But you know, when I think traditionally about, you know, sort of generics, it's a C++ template, really metaprogramming, and this implementation is a lot more to me like the Java syntax sugar.
Yeah.
Really moving, you know, from runtime to compile time.
Yeah.
Because it seems to me to be, the verbosity seems to me to be no more than doing a reflect type of and checking, you know, at runtime that my incoming types are the same, and panicking then as opposed to panicking, you know, at compile time. The real question I have here is, what does that gain us moving it from runtime to compile time?
Yeah. I think I think the reason that this is coming up now is that Go has grown to such a large developer community and has been very successful, to the point where I think the core team has now started to look at what are the actual like user complaints, and I think that really the generics implementation being done this way just comes down to better developer UX. And you said it exactly right. I mean, it's basically, it's like they took the syntactic part from the Java implementation, but instead of using type erasure, they are doing the implementation a little bit more like Rust, where there are just some constraints that are defined as the regular language interfaces. But that's a good question. I mean, the fact is that Java didn't have generics until I think 1.5, which was probably early 2000s. I know C++ didn't add the template metaprogramming until sometime in the mid 90s. I don't remember exactly when. But these are things that are not, they're not core, they're not required to be core language features. They're definitely nice to haves. So it's a good question. I don't think they're technically necessary, and we've gone quite a long way so far without generics in Go. I think it's just more, I think they're thinking of it in terms of, well, if we want to make things as easy as possible for users, people who want generics should be able to use them. And then also, I think, I don't know, like some generic containers are much easier to write, like maybe expanding what is sortable. Like, I don't know. It's a good question. It's some people are going to find it very useful. Some people are not going to find it useful.
So that actually leads me into the second portion of the same thing, and that is the main differentiator I see here is constraints.
Yeah.
And constraints, you know, it's interesting at first glance, but it almost feels like overloading. And that kind of hits me on one of the core features of Go is the idiomatic desire to do things only one way.
Mm-hmm.
And it feels to me like this just opens up a can of worms in how many different ways we can do things in terms of complexity. And I think that was one of the things that drew me to Go, was that
Mm-hmm.
after working with C++ since the early 90s, you know, with C with classes, and it's just, it was so complex, nobody wanted to get involved.
Yeah.
Are we upping the barrier to entry by doing this sort of thing?
That's a really fair question. I mean, the thing is, you know, as nice as these are to have, I don't have any doubt that if you look at, you know, and it's interesting the way that they're doing this implementation. I don't know that there's ever going to be a Go 2. I think it may be that generics just get implemented in like Go 1.20 or something like that. I think it's going to be the case that like code that's written from day one with the generics implementation is necessarily going to be a little harder to understand than Go code that's written right now. So that's a really important trade-off, and I totally agree. I think it's a trade-off that people are going to have to make. Yeah.
So I have like a question to piggyback on that. How easier is it going to be to like shoot yourself in the foot? Usually Go from other languages don't actually have, like, when you're doing a code review, you don't end up with too many places to shoot your foot in.
Yeah.
So will this add more places to shoot your foot in?
I think so. I mean, fortunately, like it's gonna. So a good way to phrase it is, I think maybe Robert Griesmer, one of the draft design authors, or someone in the Go core team, when they first started discussing this, was saying that it was sort of like a cap theorem trade-off thing, where you're going to slow the developers down, you're going to slow the compilation time down, or you're going to slow the runtime down when you implement generics. And so I think they're doing their best to work around it, but I think it's going to slow developers down a little bit. So not so much that you'll shoot yourself in the foot in terms of writing incorrect or non-memory safe code or something like that, but it's more going to be, you're going to get more of those type check failed errors, for example. So like you might have to argue with the compiler a little bit more. I think that's the way that I see it if they implement it this way.
If you don't mind me making a comment on this as well, I almost think that it's going to improve that situation, because while it syntactically is more complicated for the developer to read and the barrier to entry may be greater, once understood, I would suggest that the compiler catching things up front would allow things like static checks more effective.
And on top of that, you know, I think, yeah, definitely like everything that's caught by the compiler is like a unit test case you don't need to write. And the other thing, you know, one place I see this being useful is, you know, I'm sure we've all encountered, you know, libraries where there are like methods that like take interface and return interface, and you basically have to read the source and then pause it in a debugger to figure out like what on earth to do with the return type, right? Unless someone wrote really good documentation. And it seems like a lot of those could be replaced with, you know, this, or a lot of things where you've written like auto-generated half a dozen methods that just take and return various types of ints, but do the same thing, right? So I can see this making like, yeah, library usage much more straightforward.
Yeah, and that's been my experience writing a lot of Rust alongside Go, is that I prefer the trade-off of the compiler rejecting my code much more often and much like earlier and more often to get the correctness right in the compilation step. And even though it can be painful to take the time to like constantly be rewriting my types and data structures and algorithms in a way that will finally like meet all the requirements of the compiler, but I like that trade-off, because then I don't need to think about it after that. And I agree. I think it will. yeah, I think it's the right trade-off to make, I guess, is what I want to say is if you're going to be using these types of generics and it's going to make the syntax and reading code a little bit more difficult. But if that means that you work with the compiler a little bit more upfront, but the code is more correct and has is correct in a broader scope of domains for your program, I think it's a worthy trade-off.
And I got to tell you, I've recently been working on an open source project for diff and patch and merge on structured objects, and the heavy use of reflection can just make you mind-numbing.
Yep.
This sort of thing is what actually piquing my interest, which is why I was interested in the generics in the first place, to be able to kind of make that interface much more clean.
Mm-hmm.
However, on the same token, my question also stands is where's that trade-off? The things that are appealing to me, or once I strip that binary, there's almost nothing there. It's small, it's fast, and yeah, it may be a little harder to read, but it's pretty safe. How much am I going to gain by going this route in complexity?
Yeah, it's a good question, and that's maybe a point of that's a good way to look at where the generics implementation would be useful is if you're heavily relying on reflection, those might be. But yeah, in that case, it's really just a syntactic change. It's not like you're really gaining anything. So it's a good question, and I think this is why this is has been such a controversial topic in the Go community, is that there is a lot of valid trade-offs where, I mean, like I said, up to this point, like I know where I work, we could have made a great use of generics to simplify our code base quite a bit. Two or three core packages would have been much simpler and much easier to debug, but not everyone has those specifics, and sometimes the trade-off is not going to make sense, and it's just going to make things a little more complex. And I think that's why they've waited this long to try to implement generics, is that the core team has been very reluctant to sort of expand the surface area of the language, and especially expand like the mental model space of the language. So it's an important trade-off to think about.
I've also had an experience on several occasions when new core features of languages come out. And a great example would be Java streams. There's a litany of people deciding that that is the only way they have to go because it's something new.
Yep.
And I guess my fear for this here is that, there are valid places, especially with the concepts of constraints, that this could make huge differences when you're doing something heavy with reflection. But littering this throughout otherwise simple code may be more harmful than good.
Yeah, that's a fair concern. I think definitely when and if the generics implementation is a part of the language, you're going to see a ton of open source libraries that are like generic container types for no reason. That's going to happen. That's a really good analogy, actually, the Java streams thing. And I think any new Java release seems to, at least as a bitter Java developer myself, I think anytime any of the new language features come out, people try to jump on them and not necessarily think of the trade-offs in the right way. That's a fair concern.
Awesome. Oh, go ahead, Chet, sorry.
I was going to ask, on the flip side of that question, has there been any work done for marshalling and unmarshalling unstructured data types?
That's a good question. They left that, as far as I know, from what I read in the draft document, they left that out of scope. I don't recall anything about marshalling and unmarshalling. But that's a good potential use case. Especially if I know like marshalling and unmarshalling JSON can be pretty painful. So that could be useful.
Well, I know we're nearing the end of our time. Were there any other questions that anyone wanted to bring up? Okay, well, thank you so much, Damien, for walking through this. I know this is super helpful. I'll go ahead later today and send out just kind of a follow-up email to everybody. We'll be looping up with you guys just to send out the recording later on. And then also we actually have an event next Wednesday at the same time. It's going to be one led by a software developer named Kyle Yost, and he's talking about mocking techniques in Go. So if you're available and interested, you all are welcome to join for that. So I'll send the link out for that. And also I'll send a second link, and that'll just be a place where you can put in your name and email and select what your interests are, because it would be great just from my end to know if you're interested in doing more of these huddles. And if so, that way I'll know like which languages you would want to learn about, that kind of thing, because we'll be doing more of these in the next few months. So, but yeah, Damien, really appreciate you leading today's discussion. It was great to see all of you. And I hope the rest of your day goes well.
Yeah, definitely. Thanks for having this talk, Damien.
Yeah, great job.
Yeah, thank you.
Thanks, Damien.
Thanks.
All right, bye everyone.
Thanks.
Bye.
Take care.